Hey everybody, it's Tony D, and you're live from my desk. So we're going to hack on the Circuit Playground board and play around with some stuff that I've been doing using Firmata, which is a way to control the board remotely. So let me switch to the desktop or the workbench scene, and we can take a look at what I've got here. So basically just have the Circuit Playground board here. This is the first revision of it, which was kind of the initial run of just getting the components on a board and seeing how it works. And so you can see, like, here's the programming header on the back here that we kind of soldered on to load it up with the initial firmware. But you might have seen, if you haven't seen them already, there's some good streams about how the board was designed and what it's intended to do. And actually just earlier today, so if you look at Twitch, there was a live stream that Lady Ada did on dealing with the bootloader and making it available with USB mass storage. So lots of cool stuff that we're planning with Circuit Playground. What I've been playing with, though, is Firmata, which is an Arduino protocol for controlling a board remotely. So you can load a Firmata sketch on an Arduino, and then you can go in and control the board using like a script on your computer that might, set like digital inputs and outputs or read analog input values. Or you can, I think there are even like graphical programs you can use to talk to Firmata. So a lot of cool things you can do. Now the big thing, the big scenario we think about with this and Circuit Playground is, what if you want to do programming of hardware, but you don't want to do it in C or some of these real low-level languages? What if you want to use JavaScript to light up LEDs and things like that? And there are some boards, like dedicated boards, that can run JavaScript interpreters, even like the ESP8266, it can run MicroPython. So there are ways to use high-level languages, but it's usually a little more expensive. Like, you need faster processors, you need a lot more memory, and things are sometimes more limited. So Firmata is kind of a good way to use really inexpensive boards like the Arduino and have something like a Python program or a JavaScript program run on your computer and then talk to your Arduino just using that serial port and then the Firmata protocol. And that way you can do things like, say, I want to light up the neopixels on the board. So I'll have a Firmata command to change the color of pixels and push them out there. So I'll get started. Let's switch to kind of the desktop view, and we'll see kind of what I've got here. So I've already started a little bit with this. I have actually on GitHub an initial run at like a quick demo of using Firmata. And so it's in the Circuit Playground Firmata repository. And I have two things that I have inside of here. So there's the actual Firmata Sketch, which is what gets loaded onto the Arduino. And this is just based on the sketch that is included in the Firmata library. So it's like the standard Firmata. It lets you control the digital pins, the analog pins, do some basic stuff like talk to I2C devices. And I've taken it and I'm starting to extend it to put in my own custom commands. Because Firmata doesn't know, for example, how to light up neopixels. Like, there's no command built in for that. Or we have an accelerometer on this board, the LIS3DH, and Firmata doesn't know how to talk to that device. So I need to make my own little custom Firmata sketch that says, okay, here's how you can light up the neopixels on the board, or here's how you can talk to the accelerometer and get back like a XYZ acceleration value for it. So that's what I've started here. I have a few of the commands kind of implemented already to talk to a few of the devices, but we'll kind of run through maybe adding some extra commands here, which is kind of useful and really interesting if you're using Firmata. Like, it's good to know how to extend it, because the protocol does have some ways that you can plug in your own logic and add your own commands to it. So we'll kind of see an example of that here. And then let's see. The other thing in the library are some Python code examples that I have of talking to the board. And I'm using a really nice little Python library called PyMata, which is actually, it's from GitHub here on this repository. And it's a great little library. It pretty much implements the full Firmata protocol, so it can talk to any device that has a Firmata firmware and control all of its inputs and outputs and things like that. And so I've just taken that and I've built a real small layer on top of it that I'll walk through that's Circuit Playground specific. And so there I can plug in real nice functions to say, okay, I want to read the accelerometer value, and it can know how to create the command to talk to the Firmata board, the Circuit Playground board, and get the acceleration values and things like that back. So the code, it's hopefully much more simple than what you would write like on an Arduino, because when you're dealing with Python, you don't deal with memory allocation and stuff like that. So in less lines of code, and maybe simpler lines of code, you can do things that you can also do in Arduino. So let's see, I'll start, let's look at the Firmata sketch itself in the Arduino IDE, and I'll just kind of run through a few of the commands that I've added. Or actually, maybe before that, let's jump into the examples and I'll run them and kind of show you what we've got. So let me switch to the workbench view here. So okay, so we've got the Circuit Playground board over here, and in the desktop up above, you might not be able to see this, but I'm just going to run some Python scripts that I have inside of here. So one interesting thing, and actually here, let's switch back to desktop view. So I've got the board connected, the Circuit Playground board, to my computer, and it's just showing up as a serial device. So I'll go in and we'll see all the serial devices. So it shows up as, let's see, oh interesting, it's not there right now. So let me unplug it and replug it back in, see if something got messed. Oh no, sorry, it is there, but we'll just see if it's here still. So it's this TTY ACM6 device, which this is kind of annoying in Linux. Like, you get all these default serial ports, and you kind of have to know the TTY ACM devices are USB CDC, like a modem. You might also see TTY USB devices. Those are like a USB serial device. It kind of depends on your distribution too. I'm using Ubuntu here. But so this is the device. It's the serial port of the microcontroller. And if I try to open that in like the Arduino serial monitor, I'm just going to get some garbage back, because the Firmata firmware knows how to talk kind of its protocol, and it's a binary protocol. It's based on MIDI, so you can't really talk to it with text. So it's not that interesting for like a human to look at. But so the examples I have in here, I have one that reads data from the accelerometer, so it'll grab like the acceleration values and print those out. I have another that lights up the neopixels. One that does the tap detection in the accelerometer, so that's a nice little feature of this accelerometer. You can tap it, and it has a little register that says, hey, how many, what tap did I detect? It was like a single tap, double tap, so you don't have to do a lot of the logic and math to figure that out from the acceleration values. There's tone playback, so I can play back tones on the little speaker that's on the Circuit Playground board. There's a button example that just reads the state of the buttons to see have they been pressed, things like that. And then a temperature and a light sensor example, where there's a temperature thermistor on here and a light sensitive resistor also, where you can read those analog values and see, get some sensations of like what's happening in the world. There's also a microphone on here that I don't have a demo for yet. Maybe later I'll do a demo for that, but it's just a simple little analog microphone that goes to an analog input. So it's pretty straightforward. It's just like reading the light sensor, for example. So let's run the NeoPixel example, because that one's kind of cool, a little more visual. So maybe I'll show it first from this view, and then we'll switch to the workbench zoomed in. But just to run this example, I'm just going to run Python and my pixels.py script, and then I have to tell it the serial port that my Circuit Playground board is connected to. So dev tty acm6, and I'm going to run this, and it'll print a little bit of initial startup text. So this is Firmata going in. It's connecting the device. I think it does a little bit of an exchange. I haven't looked into it much. And now you can see, okay, it connected, and it's animating the pixels for 10 seconds. So maybe let's jump back to the workbench view so you can kind of see here the colors of the pixels. I'll run that again. Oops. And again, it might get blown out a little bit by the lights on the desktop over here. But it's connecting again, and so you can kind of see it's doing a little rainbow cycle. Now, the important thing to note here is that these pixels that are being lit, they're not being controlled by the Arduino. So like normally if you look at the NeoPixel library and you're running code on an Arduino, your sketch itself is doing all the animation. So it's looping through and saying, okay, I'm going to light this pixel this color, another pixel another color. What I'm actually doing here is I'm actually having code in Python that's calling a simple little setPixel API. That turns into a Firmata protocol command that goes down to the board, and then that actually lights up the pixel. So it's basically sending like a single pixel light every couple tenths of a second to animate the pixels. So it's the code on the computer that's actually controlling that little animation that you saw there. And so let's maybe dive into that code first. I'll walk through all the examples, maybe just kind of do them in order here. So let's switch to the desktop view. Well, let's do desktop and workbench. So let's take a look then at this NeoPixel code. So it's in this editor window here, I have basically the code that's on our GitHub repository, and it's the pixels.py example here. And it's it's hopefully pretty simple. I mean, it's maybe not super simple if you've never done programming before, but I'll kind of show you. It's really just a few function calls you have to make to talk to the Circuit Playground board. So at the top of the sketch, I'm doing some imports, and these are just telling Python that there's certain libraries, like some standard libraries I want to use. And then this Circuit Playground import, we'll look at that in a second. It's basically a little class that I built to simplify talking to the Circuit Playground board. I do a quick little check to say, have you specified the serial port, and you can fail real quickly if not. And then basically I create that Circuit Playground object that I imported above, and I tell it the port. So then that kind of initializes my communication to the Circuit Playground board. And then the actual animation, I just set up a little array of colors, like in rainbow order here. So I could add other colors to this if I wanted. And this just tells me which colors to use. And then in my animation, I basically go through and light each pixel up, just incrementing the colors. So like the first pixel will start red, the next one will start orange, the next one will start yellow. And then after I loop through and do all those pixels in this loop, I go back and I add an offset and say, okay, now do the second pixel in red and the first pixel, or the third pixel in orange. So that's kind of how you see that animation where the pixels move around. I'm just controlling an offset in this outer loop here and adding that to the pixels that I'm changing the color, and using kind of the modulo operator here. This is a really handy way to constrain a value to be within a certain range. So like this range goes through 100. I only have 10 pixels on this board, and so by moduloing it with the number of pixels, then I'll get a value that goes from 0 to 9, which is basically like the pixel location. So the code then that actually does that animation in this inner loop here, so I loop through all 10 of the pixels, and I pick a color. So I do a quick little lookup in this table here based on the offset and what kind of position I am in this inner loop. And then I call this set pixel function here, and this is the important thing. This is actually sending that fermata command down to the board that says, hey, for pixel 0, for example, the first time it runs this loop, set it to this color RGB value. So the colors are the red, the green, and the blue components, and they just go from 0 to 255. So it sends that color down, and then the Firmata sketch that I've modified reads that custom command and says, okay, this is a set pixel command. I need to parse out which pixel I'm going to light, what color I'm going to use, and then it goes and sets that pixel to that color. And then the next command it calls after it gets through a loop of that is a show pixels function call, which is another custom Firmata command that goes in and says, okay, now that I've set all those pixels, it doesn't actually light the pixels up, so it just changes the pixel color in a buffer in memory. So that's a good way where if you want to do like an animation, you can change all your pixels in the buffer in memory, and then only when you call the show pixels function will it dump out that buffer and say, okay, now the pixels have been lit, so that you can kind of light all the pixels at once, and you don't have to go in and like update the pixels constantly in here. And then I just do a time.sleep, which is basically like the delay function, but in Arduino, but in Python. So I'm just saying, okay, sleep for about 100 milliseconds here. So this is floating point value in seconds. So this is 0.1 of a second here, or sorry, so a tenth of a second rather. So that's pretty much it as far as talking to the NeoPixels. There are a few other functions I have here, like one that'll clear all the pixels and turn them off. And then another that just kind of closes the connection to the board, which is kind of good practice to do some cleanup here. But that's really all there is to this script. So it's pretty straightforward as far as just calling that set pixel function. So let's dive a little bit deeper and maybe look into this Circuit Playground class that I have that kind of wraps up the functionality of talking to the Circuit Playground board. So again, it uses the PyMata library, and I've kind of inherited from the base PyMata class and then added a few extra functions to it, because the base PyMata class, so this is the documentation for it, it only gives you functions like digital read, digital write. It doesn't give you like that set NeoPixel function. So that's stuff that I need to add on to it. So by inheriting from it, I can basically extend it and say, okay, this Circuit Playground object is a PyMata object, so it's going to have all of these functions that PyMata implements, like digital read, digital write, analog read, write, that type of stuff. But in addition to that, I can add my own extra functions to it that call things in PyMata internally to control the board. And so I won't maybe dig too deeply into this, but I'll show you the pixel functions here. So like the set pixel function, clear pixels. So all these functions are really doing is just sending a sysx command, a system extension, using Firmata. And so basically Firmata is based on the MIDI protocol, which is a way that devices, like audio devices, have kind of communicated and controlled each other. It's been around for a long time, since like I think the early 80s or so. And it's an interesting protocol. It's basically it uses bytes, but when you're sending data around, it only uses the last 7 bits of a byte. Like the highmost bit is used to control if it's a data or a control signal, which makes it a little challenging. And so that's kind of why you see in this code above here, I'm basically taking in the pixel that we want to light, the red, green, blue value, and I'm going in and saying, okay, what let's convert those values to bytes that I can send down using this custom command. But I have to go in and actually say, my red value is a byte, so it goes from 0 to 255. It uses all 8 of those bits, and I need to actually turn that into 2 bytes because I can only send 7 bits of data at a time. So this one red value, even though it could fit in a single byte, I have to turn it into 2 values when I send it down using that system extension command. And so that's kind of what this logic does here. And this is a good kind of little point that might trip you up in Python. When you're dealing with fixed length values, like an integer that's only 8 bytes long or 8 bits long. So Python by default uses 64-bit integers as kind of the default numeric storage. Python 3 I think changed that. I think it's like arbitrary size integers, but I'm just using Python 2 here for now. And so the trouble is when you get a numeric value, especially if it's like a negative value, you actually might have more than just 8 bits inside of there. And so if you try to do math on that, assuming that there's only 8 bits of data, things start going wrong pretty quickly. Like you'll get, if you have a negative value, it's a 2's complement value where there's basically a 1 sign bit that's extended through it, and so you can start getting really funky values when you deal with that numeric data. So I'm basically anding it with OXFF, so that's basically a 1 in every bit of the lower 8 bits of a byte. And when I do that AND command, it says, okay, strip off everything except the lower 8 bits of this numeric value. And so that way I can know that no matter what that value is, if it's negative or whatever, I'm only going to get those last 8 bits. And so I've effectively converted this numeric value from like a 64-bit integer to just an 8-bit unsigned integer here. So it gives me kind of the raw value. And you'll see that a lot in code in Python that deals with embedded devices and does a lot of bit manipulation and things like that. So that's what I do here. And then inside of here, I basically just do a little bit of bit manipulation to say, okay, I need to pull out the top bit of red and say, okay, this is my high order bit, and that goes into one of the Firmata command bytes. And then the next command pulls out the lower bits and says, okay, grab the next values. Now inside of here, so I could send 2 bytes for every byte of color because each Firmata byte is only 7 bits long. But I figured, maybe that's not super efficient. Just for sending 3 bytes, maybe not so bad to do that. But I went a little bit further, and I actually tightly packed those values into just 4 bytes here. So, I have red, green, blue values, so that's really just 24 bits of data. And then I've put that into 4 bytes, which would be 32 bits of data, and those can be transmitted to Firmata using just 7-bit bytes effectively. So instead of extending it out to 6 bytes of data, I've extended it to just 4 bytes of data, and then packed all the data in really tightly so that when the red bits end, the green bits start immediately after that, and then the blue bits start right after that. So I've basically just done some bit manipulation to convert from those 8-bit values into a little 7-byte or 7-bit value friendly, 7-bit friendly values. So then I call this sysx command, which unfortunately this is using an internal part of the Firmata library. So one unfortunate thing with Firmata is that it doesn't look like it's really designed to let you extend it super easily. You kind of have to call an internal function. The nice thing about Python is that it doesn't care about, like, there's no real concept of a private function that you can't call when you inherit something. If you know the name of a function, you can call it. So like this command handler is an internal object to Firmata, and I can call functions on it. So I basically looked at the Firmata source code, saw what they're doing. Now, this works, but it's dangerous. I mean, there's a reason why the Firmata author made this a private, quote-unquote, variable, or one that's not documented. It's because they might change that interface in the future. So it's just a risk you have when you're dealing with things. Ideally, Firmata would probably have some way that I could call this send sysx function myself, but unfortunately it's not there. So I just kind of have to go in there and just hack it myself and make it work. And this command, it really just says, okay, I want to take in a sysx command in Firmata and MIDI. You can basically pass in one byte that identifies your command and says, okay, this is what my custom command is. And so I can send any value inside of here. And I'll show you up above, I've defined some special values that say, this is the neopixel set command. And then you can actually pass in the bits of data here, and just as an array of the bits. And so that's what I'm doing here. Now the CP command value, this is a little define that I've set. So the way Firmata works is, if you do a sysx command, the very first bit or byte of that sysx command should be the identifier for your commands. So like if you could go in and say each of my NeoPixel or each of my Circuit Playground commands has an individual top order command identifier. But the problem is there's a limit to how many sysx command identifiers you can have. I think it goes from like 0 to 7F or something like that. So I don't want to go in and start building all these huge high-level commands that other Firmata, libraries and things might use themselves, and then you might conflict with them. So I basically have one high-order command, the Circuit Playground command, that says, okay, OX40, if there's any sysx command that starts with OX40, that's my command for Circuit Playground. So the next byte of data then, just the convention that I'm setting, is my subcommand. So I defined a bunch of subcommands that say, okay, if I want to send a pixel set command, I need to send a sysx command that starts with my OX40 Circuit Playground identifier command byte, and then after that, the next byte is my pixel set subcommand. And so I can define a bunch of pixel subcommands, and I don't have to make these high order commands where I might be limited by the available commands in Firmata. So this way I effectively have up to 255 commands that I can create myself inside of here. So I have a pixel set command, pixel show command, clear command, and those all map directly to the functions that I've added to my object here, my Circuit Playground object. So there's the set pixel command. Now clear pixels is a lot simpler. It's just a command. There's no real parameters that it takes. So it just sends down my Circuit Playground command and then the pixel clear subcommand inside of here. And same thing for show pixels. So there's nothing crazy inside of there as far as like having to convert parameters around. So that's the code so far for here. And let's maybe jump to the actual sketch, and I'll show you how I receive this command now and actually do the processing. So this sketch, it's based on the Firmata standard kind of example sketch, and you'll see it's really complex. Like it's almost 1,000 lines of code, which for an Arduino sketch is pretty complicated. But really at a high level, all it's doing is just implementing the Firmata protocol. So it's looking for all the commands that Firmata exposes, and when it gets like a digital write command, it goes in and calls the Arduino digital write command, things like that. So there's kind of a method to the madness of all the code inside of here, and it's just doing some kind of basic parsing. And the interesting thing that I want to look at is how I can plug in my own system extension command parsing, and I'll show you where I did that. So it's inside of the class. Let's see, down here. There's a sysx callback function, and this gets called by the sketch when it gets a sysx command and it needs to process it, because the Firmata protocol itself actually has some system extension commands that it natively implements, things like I2C access. It'll go in and it actually implemented those as sysx commands. So you can see this is exactly where it does that processing. So it's looking at the command byte and it's seeing, okay, this is an I2C request, so I need to go in and do some I2C processing. Now I put in a little case here that says if I get my Circuit Playground command byte, which is that OX40 value, then go to my processing here. So I made a little function that's called the Circuit Playground command, and this takes in basically the subcommand. So it expects to see a subcommand, at least one extra byte, and then all the parameters, all the extra data it gets, it also passes into this. This is just to keep the code a little bit cleaner, so I could put all of my subcommand processing into another switch statement, and you can actually see the I2C processing down here does exactly that. The problem is, like, when you get a function that starts to have all this extra logic added to it, you know, this sysx callback function is pretty long. Like, this is, I don't know, this looks like about over 100 lines of code, and it gets really hard to grok a long function like that to understand it. So I like to break things out and, you know, make functions that are at least dedicated to like one thing. You know, ideally it fits like on a page, so you can actually read the whole thing. But, you know, keep things a little more isolated so that I'm not throwing all this logic in here, because that's just an easy way to get bugs where, you know, you forget that you have code in certain places and you don't update it all. So my circuit playground function, this is where I actually go in, then it gets passed in the subcommand and then all the extra data that was sent in here. So you can actually see I just have a big case switch statement that says, okay, here's what happens when I get that pixel set command. And it goes in and says, okay, I know that I need to parse out that NeoPixel data that was sent to me. And that's kind of what this code does here. And it's kind of ugly because I chose to do that real tight packing of data. So it has to go in and pull out the red data and save that as a byte. And so to do that, it has to pull out, you know, the 1 bit from one of the bytes of data, and then 7 other bits from another byte of data. So that's why you see all this bit shifting and anding. You know, it's basically just pulling out the values that I set before. And then right below here, it's just calling our NeoPixel library and saying, set the pixel color using the pixel that was sent to me and the red, green, blue values that were sent to me. So there's no real crazy magic to this. You know, I'm just using the NeoPixels like you would in the example sketches. You know, I'm just dealing with the parsing of all the data here to pull out my custom command logic and stuff like that. So you can see like the pixel show and the clear commands here, they're simple. They don't have to look at any parameters. And so they pull out that data. And so that's kind of what's happening here. Now, the nice thing is, like, this looks really complicated, but for most users, they never need to really touch this Firmata sketch. You know, it can have all this parsing logic inside of it, and then really what people will use are the Python's sketches, and it doesn't have to be Python, by the way. You can use anything that talks to Firmata. So like there's JavaScript, for example. I think Johnny 5 is a framework for that. So, you know, this is the code here in my Python sketch that talks to Firmata. And, you know, this is nice and simple code. The sketch itself on the Arduino, it's a little more complicated, but that's okay, because that's not the goal here, to, you know, make this a simple sketch. This really just needs to be efficient at parsing the data. So let's see. Let's jump real quick. I'm going to jump to CatCam because I forgot I need to open up the comments to Twitch, so you can kind of see there's the cat. She's right over here, happily asleep. So usually she wakes up around this time, so we might see some CatCam action in a second here. So let me open real fast to make sure I get the Twitch comments, because I noticed I didn't have those. I'm still a little bit new to Twitch streaming, so this is kind of fun learning everything. And especially, so it's not just Twitch streaming you have to learn about. I'm using OBS, the Open Broadcast software, which is kind of a neat way to broadcast stuff to Twitch, but that has a whole learning curve too, which is kind of interesting. Let's see, let me log in here real quick and get to our chat. And this is also a good time, if you have questions, throw them in the chat, and I will be there in a second to see this. Okay, cool. So I've got the chat here. Let me pop this out. Okay, cool. I think I'm in chat now. So let's jump back. So we'll come back to CatCam in a second here. Let's go to the workbench and the code here. So, okay, let's do another quick little example. So we looked at NeoPixels. Let's do the tones, the speaker on here, and let me switch to the desktop view. And there's not much we'll see. So there's a little speaker. It's this kind of big box right here on the board that might be a little tough to see. But it basically, you can use the tone function in Arduino to go in and say, you know, generate like a 440 hertz tone, you know, a note like that. So I'll play the example first. So I'm going to run my Python tones.py sketch. And again, I need to pass it the serial port, so that dev tty acm 6. And we should see, actually I'll hold up the microphone to the board here, and it's going to take it a second to, actually no, I don't need to use sudo to run this. That's the one nice thing about Firmata, is that because you're using the serial port, most operating systems let you access the serial port without having to be a root user or have, you know, like an administrator privilege. So okay, so let's run this. It's going to connect, and I'm going to hold it near the microphone here, and we should hear it run through a little scale in just a second. So it's opening. Uh-oh, that angered the cat. Hang on, let me switch to cat cam. For some reason, she really hates little piezo buzzer sounds. Uh-oh, now she's coming over here, so we'll, we've got a cat invasion. Oh, now she's at the microphone. So that was basically the tone demo. So it went through and played a little bit of a sketch to play a scale of notes, and it used a little another custom extension to Firmata that I added that lets you generate a tone and play it back on the board speaker. So let's jump through the code real fast for this. Let's go to the desktop view, and actually let's do this view of it. So let's look at that tone example. So this is the code that I just ran, and so it's real similar to the NeoPixel example again. I have to import the same stuff. I do the same check to see that I have a serial port. I create the circuit playground object, and now I say, okay, let's make a scale of notes to play. And this is actually just the raw frequency values for certain notes. So this is like a C major scale. And the nice thing is you can actually find these. Arduino has a little tutorial on the tone command, so I pulled those in. So this just goes through and plays the C4, D4, E4, these notes kind of in order. I set a duration for how long I want each note to play, and this is in milliseconds, so this is like a half of a second. And then I just go through and I play all of those notes in a loop here. So I loop through my scale, and I call this board.tone function that we'll look at. And then in between the notes, I do a little bit of sleeping. So I sleep for, let's see, what did I, oh yeah, so I divide my duration by 1,000 and say, I add a little bit of padding to it. So, you know, I sleep for about, less than half a second. And then I go on after I play my scale, and I play a tone, and I sleep for a little bit, and I stop the tone. And so there are two ways that I've set up the tone function to work. And actually, Firmata itself seems to have an extension to support the tone function, but it looks like the version of Firmata that Arduino uses doesn't have that implemented yet. And I'm still not totally sure why it's not in there yet, but it's, eventually I think Firmata will have a native way to play tones. But for now, I basically created my own commands, also because the speaker is on a specific pin, and so by making my own tone command, I can just assume that I know what the pin is to talk to the speaker. Whereas if you're using Firmata, you'd have to say, oh, I actually want to send a tone out on, the speaker itself, which is on pin, I forget which pin it's on. Oh, it's, digital pin 5 on here. So that kind of simplifies the interface to the code that I've created here in Python. But so the two ways I have to use the tone function, one, you pass in the frequency of the note to play, and then you also pass in the duration, so how long you want that to play in milliseconds. And I think this is smart because one problem, you could imagine that you just have a function that says start playing the tone at a certain frequency, and then another function says stop playing the tone, and I actually have those functions in here. But the problem could be, what happens if your sketch runs, or your program runs rather, it tells your board to start playing a tone, and then it crashes, it dies. Your Firmata board is just going to keep playing that tone. It's going to go on and just keep, it could be a really annoying tone that's going to keep playing. So by having a function that takes the note and the duration, it makes it a little simpler, so it ensures that tone will stop playing after it finishes. I mean, there are ways that your function could still crash somehow. Your computer could crash and it might still get stuck playing. But it's trying to be smart about not letting people do things that get you into a bad situation easily. So that's kind of one way to call it. But there are cases where you really do want to play a tone and not pass in a duration. Maybe you're controlling how long the tone plays based on like a sensor value or something like that. So I did add that function in where you can just skip passing in the duration value, and it will just start playing the tone that you pass in. And so that's why after you heard it go through the scale, it played a tone for a second. That's what this code does here. So it starts playing. I just sleep in my code here, but this is where I could put in extra logic. Like maybe I call a web service that tells me how long to play this tone or something like that. Sleep is just, pausing my program execution here. And then I call this NoTone function, which stops the tone playback. And so that's kind of a good example too if you want to control this yourself. And so let's see, we'll look at real quickly the code for this, and it's very similar to what we saw before. So, I'm basically packing a couple bytes into 7-bit friendly bytes. And in this case, I didn't do that extreme kind of packing that I did with the colors. I actually just took my frequency value and converted it into 2 bytes here. Or actually, yeah, I forgot. So the frequency value, this just gets passed directly to the tone function in Arduino. And that function apparently only takes 14 bits of data. Or actually, no, I think it takes 16 bits of data. But rather than pack more bits of data into here, we just take the top 14 bits or the lower 14 bits. I was actually looking at, this is what they do in the Firmata tone extension. They support up to 14 bits of data. So I figured I'd be consistent here because maybe in the future we do start using their function for this. So I basically take the frequency value, the duration value, convert it into 14 bits of data, which conveniently fits into 2 bytes that have only 7 bits that Firmata allows. And I just send another system extension command. And this time I send a tone subcommand in here. And then NoTone just sends a NoTone subcommand. And so in my Firmata firmware here, the sketch, here's the tone logic and the NoTone logic. Just like the pixels, it parses out the frequency and the duration, and then it goes in and says, okay, call the tone function in Arduino here, or call the NoTone function. So pretty simple, pretty straightforward, kind of easy to understand all the logic there. So, and you might hear in the background too, the cat sounds like this is kind of the time of night when she usually eats. So we'll try and make this a little bit quick so that she doesn't go too crazy. So okay, now let's see. I'll show another quick little demo. This one maybe isn't as interesting, but I have a demo for reading the temperature and the light sensor. So, and let me switch to the view with the board. Yeah, this view. So let's call the Python temp_light.py and pass it in the serial port again. And so this is going to connect to the board, and it's going to look at the light sensor and the temperature sensor. And this is actually using just the standard Firmata functions. So the temperature sensor is an analog input. It's let's see, it's connected to analog 0, and the light sensor is on analog 5. And so this is using our Firmata's, actually the PyMata library, the functions that it exposes to read those analog input values, and it's just dumping out the raw values. Now, it seems like this library only sends a value, and I think this might even be in the Firmata firmware. It only sends a value when it changes. So, excuse me, you see the light sensor is kind of changing. There's maybe a little more noise to that sensor. And the temperature sensor, we don't see it here because it hasn't really changed. So my example code here, my sketch, or my program rather, it's just grabbing values and printing them out. So you can see the light sensor. I'll hold my hand over here, and you can notice all the values go down. It actually dropped down to 0. And actually my hand being here just warmed it up a little bit. So you saw the temperature value kind of fluctuate a little bit. And if I pull my hand off, now you can see it jumps up to a much higher value. Actually, if I hold this in front of a light that I have here, it goes really high. So the Arduino ADC only goes up to 1024. So we're almost at the max value in front of this light here. Now if I hold my finger over the thermistor, let me find that thing here, we should see the temperature value kind of go up. And actually, let me hold my finger over the light sensor so we kind of quiet that down, hopefully. Well, not super quiet, but you can kind of see interspersed between all the light readings are temperature readings here. And if I pull away, it kind of cools down, and we might see it slow down a little bit. So this is kind of cool. This doesn't map directly to this is my temperature in Celsius. I haven't put that into my code yet, but that's in an example for the Arduino library that we have. It does that conversion. You just have to do a little bit of math for the thermistor. There's like a certain equation to convert from that kind of raw ADC value to your actual temperature value inside of here. So let's see. Let's jump through the example code for this. Let me stop this sketch. And let's look real fast at that light, temperature light example here. So again, just like the other examples, I do the same kind of setup for my Firmata, the circuit playground board. And then I define two functions. So I have a temp data and a light data function. And these just print out the value that I got. Ideally, I should extend this to say, okay, now that I have my temperature data value, let's do that equation to actually get like a value in Celsius here. But this is something maybe for the future that I'll extend. Same thing for the light sensor. And then I call the set pin mode function to for these two analog inputs to be an input and an analog input. And then I also pass it the function to call. And so it's kind of all internal to the way this Firmata library works. Once you set up this pin mode and you say, hey, analog 0 is an input, it's going to start streaming that data back over the Firmata connection to my code here. And so every time it gets a new reading from the board, then it's going to call like the temperature data function or the light data function here. So it's a little bit asynchronous. Like if you're familiar with a lot of JavaScript programming, you see this kind of paradigm a lot where you give a command a callback and it calls your function when it has new data here. And so that's why the actual main loop doesn't need to do anything. So it just sleeps forever. And it's just assuming that it's going to be getting that data back from the board itself. So it looks like the cat wants to join me. I think she's mad. She probably wants to eat right now, but we'll kind of speed through this a little bit. So that's the code here. This is nice in that I have no custom commands I need to deal with. I'm just using the built-in analog functions in Firmata. And so there's one more example I'll run through real fast also. So let's run a button example. And yeah, this is a good view for it. So let's do the button example, and I have to pass it the serial port again. And let's run this sketch. And so this one basically, it's going to listen to the buttons. So there are two buttons, two push buttons on the Firmata, on the circuit playground board. There's a left and a right one. And there's also a slide switch. And I've noticed this error before. So something about the PyModel library, sometimes it fails internally. This list index out of range. So it's looking up some kind of pin value and it's not getting a value that it expects there. But it only happens intermittently. I don't really know what's up here. I don't know if it's a bug in PyModel, something like that. But okay, so it's connected. And now it's telling me press the left button, the right button, or the slide switch. So I'll press the left button, and so it told me left button pressed, and when I release, left button released. Same thing for the right button. You can press and release. So that's kind of cool. My Python code now can detect the button presses on here. And this little slide switch, I'm going to move it to a different position. So now it's on the left side, and I can move it, it's on the right side. So this is kind of like an on-off switch for values here. So again, really cool in that I can read that from my Python code just using some simple Firmata commands. And so if I jump to the code for that one, it is in here, and it's real simple as far as it's the same setup as before. Now this time, kind of like that analog temperature light sensor function, I'm using some asynchronous functionality in Firmata where I can say, okay, I have a digital input and I can pass it a callback function so that when this input changes, call my function. So I have like a left changed function. So the left button is on digital pin 4, the right button is digital pin 19, and the switch is digital pin 21. So when any of those change, I have a function that gets called. And then part of the data that's passed into that function is the actual value of the input. And so I can look and see, and the way the circuit playground board is set up for the buttons, if the button is at a high level, if that digital input for that button is at a high level, then it's been pressed. And if it's at a low level, then it's been released. And so that's what this check here does. So it just so happens they put the actual button value. This data thing is an array, and the third value inside of there is your current value that caused this function to be called. And so I look and see, so Python is going to interpret it as like a true value if it's like 1 or anything like that. And if it's not 1, if it's 0, if it's a low value, then it'll print out this, it'll go to this print statement. And so that's all this function does. It just looks at those values and says, what's actually changed, and print out a little message about that. I think, I haven't used them, but I think Firmata actually has, or the PyModel library has a function you can call to say, effectively digital read. So like, yeah, there's a digital read command here. So this would be a little bit better. So I wouldn't have to have that callback command. I could have my own main loop inside of here. And maybe I should do that as an example later to show like using that digital read if you don't want to do this kind of asynchronous thing. Because sometimes when you get asynchronous code like this, it can be a bit of a pain to manage it. When you want to do multiple different things, you have to change the callbacks and things. So, this is maybe a more advanced example. I should go in and say, let's make a simpler example for this. But okay, so the next thing, and maybe the one thing I wanted to kind of do on the stream here, is to play with the accelerometer on here. So I've set up a couple example sketches, and they do a few things, but they're not super interesting, and I'll explain why. So let's look at maybe the accelerometer example first. So I'm going to call my accelerometer pi. And so I just ran my accelerometer sketch. I passed in the serial port again. It's going to connect to the board, and it's going to print out the XYZ values from the accelerometer. And it prints them out every 2 seconds. So in the sketch, I have a little delay. And so you can see these are the raw values. And as I kind of tilt the board, then we'll see things change. So like now the X value changed. So it looks like I rotated around the X axis. These are the raw outputs of the sensor. So I forget which units these are in, but again, there's a little conversion I need to do to convert these into like, meters per second squared, acceleration values here. Oh, here comes the cat again. So this could be interesting. She wants to be the star of the show here. So again, just like the NeoPixel code, get the cat out of the way here. There she goes. So just like the NeoPixel code, I created my own custom command. And I send that to the board. So this is this accelerometer sketch. The setup is all the same, and I basically have a function that gets called. I'm not using the tap in here, so I'll delete this. This accelerometer data function gets called when I have a new reading available from the accelerometer. And so in my main loop, basically I call this board read accelerometer. I give it a callback, and it calls this function when it's received the data back, because the way Firmata works, I send a command that says, hey, I want to read the accelerometer value, and the board will respond back with a result. So it actually sends another Firmata command back that says, here's the result of your accelerometer read. And kind of the easiest way I implemented this was just making it asynchronous, where you give a callback that gets called whenever data comes back. I could make a synchronous version of this where like I call read accelerometer and it waits to get a response and then returns the data back. So that might be a little bit easier to do. Sometimes, just you wouldn't have to have this asynchronous callback. But for now, I want to use it in an async way because I want to extend this. So the way it works right now, I call that read accelerometer function and it sends me back a value. But it would be nice, kind of like in the analog input example or the temperature and light sensor, if the board itself could stream that data to me. So like, multiple times a second, it could send that accelerometer data, and then I could have a function that's set up to receive that data, and that would be called all the time. Because in my main loop, I could try to just constantly call read accelerometer. The problem is that has to turn into a Firmata command that has to get sent down to the board. The Firmata sketch has to parse that data, actually talk to the accelerometer, pull out a new reading, then create a new Firmata command to send back to my computer. So there's a lot of time that's kind of wasted there in that conversion, and that limits how quickly I could receive data, because I could only receive data as fast as I can send a request to get it. Whereas the board itself, the Firmata board, the firmware, it could send data a lot faster than that, and I can just wait to receive that data. And so that's what I want to do in a second here, is actually add a new command that says, okay, start streaming accelerometer data, and then receive that data itself. And I'd also have a similar command to stop receiving and stop streaming that accelerometer data. So you can basically turn on streaming the accelerometer data and then turn it off when you want to get some readings for it. And the same thing I've done for the tap detection on the board. So I'll run this example real quick, and we'll see this example actually doesn't work well at all because of the way I'm trying to use it in this kind of synchronous manner. Like I really should be streaming this data back, because the way it works, there's a little register on the board that holds the tap detection state, and when that gets, so it'll read the tap detection state, and it's basically giving me back, here's the, I actually have some debug output in here because I actually was just working on this before here, but it's telling me here's the tap state that I'm getting back is 0. And that means that it hasn't detected any tap. Now if I tap the board, I might be able to get this to catch something. So you saw I got a tap detection state of C. So that means the board detected a tap. But you saw I was tapping this board a lot, and I'm not getting any results. Okay, like I happen to get one result there, maybe another one there. And the problem is my main loop here is reading the tap. So it's reading that tap register value, and then it's sleeping for 2 seconds. And if I get a tap during that time, I'm going to miss it because I'm not reading that register. I think there's only a short amount of time that it keeps that register value. So I need a way to basically constantly read that tap register and stream it out to my program here so that it can read it a lot faster than my main loop here can grab it. And so you can see it's really not useful as is right now. So that's what we'll go in and we'll kind of start playing with extending this to do some of those tap things. So let me check questions real quick. So let's see. Have you considered code to let you auto-detect the Circuit Playground board running the Firmata firmware? That's a good question. I don't know enough about the Firmata protocol if it has like an identifier where you can say like, I am this type of board. I need to look more into it to see, because yeah, that would be nice if you could have code that can just look and see like, where is your Firmata, like is this Firmata board a Circuit Playground or not? Maybe even if it could detect like the serial port that's connected to. So like there is a custom USB vendor and product ID that we have. So yeah, there could be code for that. That's a good idea to try and detect it. And are the buttons debounced? No, I don't think they are. Although again, I'm still new to Firmata. It might debounce them internally with Firmata, but I don't think it does that logic. Well, no, actually, I think it does when I use it with this level change callback, where I pass it in this callback. I think if I'm just using the digital read function, it won't do the debouncing. But yeah, that's a good question to see how it works, because that's a big problem with switches where when you're pressing a switch, there's a little period of time where you can get some noise, especially if the switch, might not be the best one in the world. You can get kind of intermittent values where it's slightly touching it, it's not touching it, and debouncing basically says, okay, wait a little bit of time after you see it change and then read the value again for that. So, okay, so let's go in and let's actually start hacking on the code for this. So I'm going to start with this tap detection because you can see this example really doesn't work well as is. And I want to make it so that I can stream new values to my board. So I can set this up and say, just as fast as the board can send it, I want to read these tap values. And so what I want to do is I want to make a new command to kind of turn on streaming of tap data. And actually here, so this is the Circuit Playground class. These are the functions that I'm using right now, this read accelerometer, read tap. And these are just telling my Circuit Playground board, hey, do a single accelerometer read, do a single tap read. And in the actual Firmata firmware, I've implemented these down here. And so I'm just calling the accelerometer read function. I'm packing up all the bits and sending them back as a response here. So it's not too crazy. And actually, I just realized too, so this is another good example of, again, I'm still learning the ropes of Firmata. So in this accelerometer read function, I was actually, before this stream, I was running into a lot of problems because I was calling this send sysx function, which the Firmata protocol or the Firmata library implements, and I was passing it an array of bytes, but I was actually doing that 7-bit packing and unpacking myself. And I didn't realize this send sysx function from Firmata will actually take every byte and turn it into 2 7-bit bytes. So I didn't need to do that packing and unpacking. I was getting back junk values because I was trying to pack these things in and didn't realize it was packing them. So I was like double packing the data. So just word to the wise, if you're doing your own Firmata extensions, this send sysx function just takes an array of bytes and it will automatically convert those 8-bit bytes into 2 7-bit bytes that are Firmata compatible. But basically all this function does is just read the accelerometer value. It's a 16-bit value that it gets back for each of the XYZ, and it's just grabbing the 2 8-bit bytes from that and sending them down. And the tap is even simpler. It's just calling this get click function from our LIS 3DH library. That just reads the click register, which is kind of the current state of the click detection. So it changes values when it sees like a single click or double click inside of here. So, okay, so I want to add a new function that says start streaming tap data to me and stop streaming that tap data. And so my idea is then in my program, in my example, instead of calling read tap, just at the start, I'm going to say start streaming the tap data, and I'll have to pass it in a function to call when it gets new tap data, and then it can just print out the data that it's received rather than having to request it all the time. So let's see, let's start from the Python side of things. So I'm going to go in and define a new function here. So let's call this start tap. And this is going to need a callback as a parameter. So you need to pass in a function that will be called when it gets a new tap data back, a new tap response. And so what I need to do is actually save that callback. So internally in my Circuit Playground class, I have a variable that I set when you initialize it as the function, the tap callback. And so this way, I have to plug into the Firmata library, and again, I have to use some internal functions here. They don't expose these, but because I've inherited from the class, I can call all of its functions. So I set up a listener for my Circuit Playground command byte here. So this is this OX40 value, and this is telling Firmata that whenever it gets a fermata response from the board that's a sysx command with my special command byte, call my own special handler function inside of here. So this is this function that then I put in my own logic to parse out the response that I get back. So this function here is just looking for an accelerometer read response or a tap read response. It's pulling out all the bytes of data that it got, and it's reassembling them from 7-bit bytes into 8-bit bytes, and then generating the XYZ acceleration values here. And then it calls my callback function. And so that's why I need to set this callback and remember it. So I save these callbacks internally to the class. Like this underscore is kind of a convention in Python where class variables that start with underscore are private variables that consumers of your class aren't supposed to mess with. But again, Python lets you mess with them if you want to. Usually you don't want to mess with these because who's to say in the future that I don't change maybe the name of this Excel callback, and if you built your code to depend on that, then it's going to break because you depended on something that was kind of internal to the class. But so that's why I save this callback function so that I can call it in this response handler, and I pass it in the XYZ value. And so that's why in the Accelerometer sketch, this Excel data function here, it takes in that XYZ, and the logic that's actually calling that function is right here for it. So I'm going to need to put in my own logic. But the nice thing is, the way I think this tap detection and accelerometer detection streaming should work is that I'm going to tell my Firmata board, start streaming back accelerometer or tap data, and I'm just going to use my existing tap reply and read reply functions so that I don't need to add new custom callbacks here. It's just going to come back and say, okay, here's tap data, and this logic is going to process it just like if I'd sent a request for the tap data inside of here. So that's why I have the callbacks, and that's why I need to set up my callback when I call the start tap function. So I'm going to remember the callback that was sent in to me so that my response handler can use that. And so now let's actually call the internal command handler, the sysx function, and I need to send it, it's my custom top level Circuit Playground command, and then I'm going to need to send it a subcommand. And so let's make a new subcommand that's maybe Excel tap stream on, something like that. So do cp Excel tap stream on. And so now I need to pick a new subcommand value. And so all of my subcommands, like we kind of saw before, I have pixel set commands, tone set commands. I thought it kind of made sense to, my pixel value is OX10, and then I have a few other pixel commands that say like OX11 is show, OX12 is clear. Then my tone commands are OX20. So this way all of my subcommands can be kind of related. So like tone commands start with OX20, pixel set commands start with OX10. This way when I add new commands, I don't have to go in and rearrange all the values. I can slot in new accelerometer commands by just adding them here to this, OX30 is kind of my accelerometer command range. So I can get like up to 16 commands here. And it'll break down at some point. I'm probably going to need more than 16 functions for something on the board. So, maybe I could pull this out and say tap related functions are OX40, something like that. So it's, just something to think about, that build things for extensibility ideally from the start. So okay, let's make a tap stream on. Let's make this OX38, and let's make a tap stream off also, because I'm going to need that in a second. And let's make that 39, and then I'll just make all those line up. So okay, so I've got my 38 and 39, my tap stream on and off commands, and let me remember this one so that I can go down. And in my function, I just need to send this subcommand here to say, okay, start streaming the tap data. Basically send that custom system extension command. And let's make another function that's just like this one, and we'll call it stop tap. And so the idea with this one is I'm going to stop all of my streaming of tap data to my board, or to my program. Now this one I don't need a callback, because I don't care anymore about receiving that data. And in fact, let's actually set this to none. So I'm going to forget whatever callback I had before. And so that's good that, as soon as this stop tap is called, it's going to immediately stop processing tap functions, even if the board is still streaming them to me, because there's going to be a little bit of delay before my system extension command gets parsed by the board and turns off. So it's smart just to disable things from the start here. I could leave this out, but then it just means your code's going to call stop tap. It's still going to receive some data for a brief amount of time. So ideally, you probably don't want to receive the data. And let's add a little doc string. So one thing I love about Python is they built in kind of documentation as a native part of the language. So the first string value after a function defines the help text for it. And you can actually see this help text. There's a Python command to parse out the help for a class. Like there are document generators that work well. So let's say request to start streaming tap data from the board. We'll call the provided callback with tap data. So we'll leave that for now. And same thing for the stop. Let's say stop streaming tap data from the board. So okay, so those are my functions. So let's actually go in and let's make a new example that uses the streaming functionality. So let's call this tap streaming, and let's actually call my functions. So at the start, before I get into my main loop, I'm going to say start streaming data. So start streaming tap data, and let's call board start tap. And I need to pass the callback function, so I'm going to pass that tap data function, which is kind of what I was using before from that read function. Now, in my main loop, I'm actually just going to say sleep. I don't need to do any processing, because the idea is start tap is going to start sending me back these tap responses from the board, basically as fast as it can send them. So we'll just sleep constantly in a loop. Actually, let's change this. I had started the tap sketch by just copying the accelerometer sketch. So instead of this, let's actually say wait in a loop to receive tap data from the board in the background. And yep, printing tap data, we can keep that. And now to stop printing tap data. So I'm going to be smart about this, and let's actually put this into a try except finally clause. So that way, when you press Control-C in a Python sketch, it throws a keyboard interrupt exception, and that's why most Python sketches stop, Python programs stop. But ideally, when I exit this program, I want to make sure that I call the stop tap, because it's kind of nice to not leave the board in a state where it's still streaming the tap data. That might confuse things that connect to it after that. So let's put this into a try finally block. So we want my main loop inside of here. And then the way the try except kind of block works, so I could actually catch my keyboard interrupt exception. And then I could call board.stop tap. Or another way to do it, I can put a finally clause in here. And the way this kind of works, it's real similar like C, C++, or other languages that have this kind of try finally. Actually, I think it was C# has this, not C++. But basically, you can go in and say, okay, run this code. If a certain exception happens, like of a type keyboard interrupt, call this function and then move on with my processing. Or finally can be a block where I can also call board.stopTap. And this finally clause, it will call this code no matter what happens when I exit this block of code here. So if an exception gets thrown that stops the program, it's going to make sure that the finally clause here is called. Or let's say I didn't have a loop here. Let's say I just had some code that did some stuff and then finished. It will also call the board.stopTap when it's done here. So I don't know. I like the idea of putting this in a finally block because that way, it's not just a keyboard interrupt that could stop my program here. Maybe someone might kill the process, and actually, depending on catching a kill command can be kind of tricky. Like this finally block might not actually be called if a program is killed with a high enough severity. So that is also a gotcha you have to worry about sometimes. But that's such a rare case, I'm not going to worry about it. But like, let's say I was calling like a web service inside of here, and maybe it threw an exception like a timeout. If I didn't put this into this finally block here, I'd either have to catch all exceptions or catch that specific like web request timeout exception, which that just becomes a pain. Like there are lots of errors you might not know about. So we'll put in the finally block. That makes sure it gets called no matter what. And then we'll close the connection also when we're done here. So, okay, so I've got these set up. Now let's just run this. It's not going to do anything though because I haven't implemented it on the firmware. But this is just a good check to make sure like I don't have a syntax error in the code. So I called this tap streaming, and we'll give it the port TTY ACM6. It's going to connect to my board, and it should just print out that it's printing tap data and then stopping. So it's doing the setup. So printing tap data. We don't see anything. Cool. That's expected. It's good to see that kind of thing. It's at least behaving the way I wanted. As far as I know, and we won't know until I actually change Firmata Sketch. It sent that custom sysx command, and then in my firmware, in my sketch here, it got that command, didn't know how to process it, and moved on from there. So, okay, so now let's slot in the actual logic to start this streaming. So, I'm in my Circuit Playground command processing function. So first I'm actually going to need to add some defines that add these extra subcommands that I just added. So let me copy out the values that I set for those. And let's see, let's grab these two values, and we'll just create defines for these. Oops. And I don't need to use equal. Oops. Okay, so, and I'll just put a little comment here to say this turn on continuous streaming of tap data, turn off streaming of tap data. Okay, so now I know my commands, and let's go down and let's put some case statements in, and yeah, here it is. So this is where I can put in new subcommands that I want to process. So let's put in, let's see, what did I call that thing? Yeah, tap streaming on. And let's see, I'm going to put this in brackets here, in braces, and I'll tell you why in a second why I do this. You don't have to do this normally with a case statement. And let's see, let's do cp excel tap stream off. That should be what I called it. Yeah, tap stream off. And again, we'll put braces here. The reason I put braces in here, and I might not need them, but it's one kind of thing where you have to be careful. If I want to create some local variables here, it needs to have like a context to create those variables inside of. And I noticed, like, if I didn't have these braces, you get some weird compiler errors where it's like, this click variable isn't set all the time in the different cases for here. So you get some funky errors if you're trying to create local variables inside of a case statement. Now, I would actually step back more, and I should probably break out all of these case statements into individual functions that it calls, so that ideally my Circuit Playground command processing function here, like I said before, I don't like to have really complex functions that have a lot of lines of code. I want to be able to look at a function and kind of understand what it's doing. And this is starting to kind of reach that threshold where it's getting really complex. Like, I have all the command processing logic for all of my subcommands inside of here. I think ideally I should break this out and have a function that's like my pixel set function that just gets passed in all the parameters and has this exact logic inside of there. Pixel show function, which is going to be a really simple function. It's maybe I don't even need my own function for that, so I'm just calling the NeoPixel library here. But if I had my own functions, then I don't need to worry about all this weird state of you need to make sure that you have a certain context to create these local variables. For now, I'm just going to put in the case statement, but that's how I think I should refactor this in the future. So I need to turn on the tap sensor streaming. And so I need to set some global state that says start sending tap data, because I'll show you how I'm going to hook in this tap sensing or tap streaming data. Let's see, let me add a new variable here. So I have a little spot where I try to put only the Circuit Playground globals, so it's easier to kind of keep track of, because again, this is a really complex Arduino sketch. I could throw these globals anywhere, but it helps if you have a place to put these things. And actually, this last click I don't even need. This, I was playing with some stuff before as I was trying to get the accelerometer to work. So let's make a global boolean, and let's call this stream tap, and we'll initially set it to false so that we don't stream tap data when the board starts up, only once we get told to stream the tap data. So back down in my Circuit Playground function here, so when I turn my tap streaming on, all I need to do is just change that boolean. So we'll say stream tap equals true, and then stream tap equals false. So now you're probably wondering, okay, what's actually going to send this data? So I need something in a main loop here. And if I go down to the main loop of this Firmata sketch, it's going in, and actually I had some stuff where I was playing around with reading the click data before. We'll pull that out. But basically, the main loop for Firmata sketch, it goes in and actually checks to see, okay, are there certain inputs that we need to read and grab their value? It reads data, Firmata commands that have been sent to it, and it processes them. But then it also has a little spot where it will do analog reads, and I think even I2C data at a certain frequency. So you can set a sampling interval, and by default it looks like it's around 19 or 20 milliseconds. And that means when analog data is being read, every 20 milliseconds this code is going to run, and it's actually going to grab the analog value and then send it out. And so I think this is a good spot where I can put in my own streaming logic, because it kind of seems like the intent of this code here is to put commands that need to start streaming data. And then the nice thing is, I think Firmata has a command where you can change this sampling interval. And so that way, if you want to stream tap data at a different interval, just use the existing Firmata commands for that. Change your tap interval, your streaming sampling interval, and then you'll get that data at a different rate. Now that might break down when you want to read analog data at one rate and tap data at another rate. But I think that's a rare enough case that it doesn't matter. I could break out and have my own loop code that says, okay, I have a different interval for the tap detection, but keep it simple. Another interesting programming kind of principle is YAGNI, Y-A-G-N-I. You ain't gonna need it. Where it's kind of a problem that you have when you start designing something. You want to throw everything in, including the kitchen sink, and you start thinking of oh yeah, maybe I need my own custom sampling interval. But in most cases, you don't end up using it. It's code that you added that's really complex. It lives, you're going to come back to this 6 months from now and forget what this logic means. So, if it's not that important, if you don't really think you need it, don't add it to start with. And so, I'm going to keep it simple, and we're just going to piggyback on the sampling logic that they have. So let's put in some code here. Check if a tap event should be streamed to the Firmata client. And so let's look at that. Let's see, what did I call that? Was it, oops, I don't have in the paste buffer. It was extreme tap. Let's go back and just double check. So let's see, yep, up here. So yeah, stream tap. So if that's true, then I want to actually send a tap value. So let me copy out the code that I had for that from my callback function here. So, you know, this is the code right now. It gets a click and it goes and packs it into a response and then sends that click command back, or click tap response back. And so I'm just going to copy this code. Again, this is a really good case where I should break this out into a function. Maybe I'll do that right after we kind of see this thing working, because now I have two spots in my sketch where I'm doing the exact same thing. And the problem is, like, let's say I change this accelerometer tap reply value, you know, to be something else. And if I forget that I have this in two spots in my code, I'm going to change one. The other one's not going to change, and then you get awesome bugs where, you know, things aren't in sync with it. So, you know, for now I'm going to be bad, and I'm going to copy the code in here. But ideally, I'm going to break this into a function. So okay, so let's just do exactly what we did before. So we're going to call the accelerometer library getClick function, grab its output, it's just a byte. Then we're going to construct a response packet that has my accelerometer tap reply, and also send in the data that we pulled from the accelerometer, and then just send that as a system extension response back. And so in theory, and I haven't tried this yet, so we'll see if this works. This should work, fingers crossed on this one. I should be able to see results from this. So actually I need to program the board again to get this latest firmware on here. So yeah, it's all set up for that. So let's upload. Oh, interesting. Tap stream off was not declared. Oh, I must have not set the define correctly. So CP Excel tap stream off. What is this thing complaining about? Let's see. Let's go back down to this line. So let's see. Oh, duh, misspelled it. All right, save that. Upload. Okay, so it's flashing the board. Okay, so that finished. Now let's run this exact same example that we did before. And let's see, fingers crossed, it's going to start streaming out the tap data. And if it doesn't, then we might need to do some debugging and kind of see why I'm not getting back the tap data for this. Ah, look at that. So we're getting a bunch of tap data here. And you can see it's happening pretty quickly. It's happening so fast that it's just, the screen is just scrolling constantly for this. But this is good. This is exactly what I wanted. You know, I'm based on that internal sampling interval, which is actually just set at the very top. I noticed, yeah, so 19, how often to run the main loop in milliseconds. So every 19 milliseconds, this block of code here is going to run. And it's just looking at the current millis value, which is just a timer that increments every millisecond. And it's just looking to see if it's if the difference between the current time and the previous time that I ran this loop is greater than my sampling interval, then run this loop. And then be careful to set your previous sampling interval or your previous value, previous time, so that you can run the loop continuously. So, okay, so this is going to run every 20 milliseconds, 19 milliseconds or so. And then I look to see, okay, if stream tap is enabled, then start getting the data back, or start sending the data back. Now let's test out stop streaming, because I want to make sure that works. So let's make my example a little more interesting. So how about this? Let's start out by streaming to the board. Let's put a little bit of a delay in. So let's say 2 seconds, and then let's call board.stopTap. And then let's put maybe a 5-second delay, and then let's start streaming again just forever. So start tap data callback. And let's print out what I'm doing here. So let's say stream tap data for 2 seconds, then pause for 5 seconds, and stream forever. So let's print out streaming tap data for 2 seconds. Now let's say print pausing for 5. Oops. So we stopped it, and actually let's put my stop down here so that I'm kind of keeping things logically next to each other. And then now let's put in the start tap, and actually let's pull this print out and put it up here. And you know what, let's just put it all inside of this loop here. Okay, so that's the code now. So it should stream tap data for 2 seconds. Oh, actually I shouldn't, well yeah, that's fine, I can keep this here. And then it's going to stop and wait 5 seconds. So I should see in my output, you know, big flood of data, stop for 5 seconds, and then another flood of data here. So, and let's run this and see what happens. So this is always a good check, like when you're implementing something, you know, make sure each thing works. Like this is almost a unit test in some ways. Oh, interesting. Type error, no attribute get item. That's interesting. Now this it failed in the setup. This might be some of the funky behavior I was seeing with Firmata. Let's see if this reproduces itself, because it might be because I'm setting the callback to none. I might be getting the Firmata into a bad state. Huh, that is really weird why this is throwing that error there. So something is wrong about the command handler. I have a suspicion that it's this board stop getting it into a bad state. So let me actually just take out this call. Let me see if it works. It might be because I set my callback to none, but that callback isn't used here. So let's see what's going on. So it opens it. Oh, interesting. So it keeps failing with this error. So it's something internal to Firmata. None type, object has no attribute get item. This basically means that something is null that shouldn't be null, and it's trying to call, and it looks like this dispatch entry is probably null. So this get item function is actually Python's little dictionary accessor, or array accessor function is being called. So for some reason, dispatch entry is, oh, interesting. So this is definitely something internal to the Firmata board. And I wonder if maybe because I told the Circuit Playground to start streaming data, maybe it's confusing it. So when Firmata runs, it does like this auto discovery of the board. And I've noticed it's a little flaky, especially if I'm streaming that data back. I might be confusing it. Like it's probably getting a callback that hasn't been set up yet. So I'm going to unplug my Circuit Playground and plug it back in just so that it gets back into a good state. So this is a good bug. Like something probably didn't call my stop tap, or my stop tap didn't work. So we'll go back and we'll kind of see what might be wrong here with that. But by resetting the board, I'm at least going to get it back into a good state where it's not sending tap data. So let me uncomment this. This is kind of the fun of dealing with a Python library like this, where, you know, I'm just using it kind of as it's documented. I did go through the source code a little bit to figure out how to extend it, but I didn't study it in depth. Okay, so this is working. It's giving me back my response data here. It stopped for a while. Interesting that when it stopped, it didn't seem to set my stream tap. It didn't seem to stop. So let me scroll back up and we'll see if we can see the output. So in my output here, it was streaming data, and actually we should see at the top here. So streaming tap data for 2 seconds. So this is good. And actually, let me uncomment. I had some debug code in here. So let's go down, and in this response handler, I was printing out. Oh, and this is another hot tip for people, Python programmers that do a lot of embedded development. The bin ASCII library has a function called hexlify, which is the coolest name ever. You can pass it an array of bytes, and it will print out their hex value. So that's super handy for debugging stuff, because a lot of times you get back some bytes, and you could go one by one and print them out with hex, but binascii.hexlify is what you want to use for that. So, but let me comment that out because that's just confusing stuff here. So okay, so it read for 2 seconds, and then let's see. Oh, okay, so I'm just getting, it actually did work. So it's pausing for 5 seconds. My problem was, and you can actually see, I see my CP response being printed out, but I don't see that receiving tap data. And that's because the debug code I had in here was at the very start of my response handler. That's a good spot to debug that kind of stuff. And then when it gets down and actually calls my tap callback, that's where I have my print command in here that says, okay, I'm going to receive my tap data. So let me redo this again. I'm going to unplug and plug the board back in just to make sure it's not in a bad state. And now let's run this again. And we should see it actually pause for a second there now that I took out the debug output. So let's see, it's going to open this. So receive the tap data, pausing for 5 seconds here, and then we should see a flood of tap data right after that. So yep, there it is, and this runs forever. So I'm going to press Control C. Now it failed with a keyboard interrupt. That should trigger this finally clause. And actually, let's put a print statement in here, stopping, to make sure that this is actually getting called. Because I think that the board is actually probably still streaming that data. And in fact, I can check real fast. Let's open that serial port and see if it's like flooding me with a bunch of junk data. So dev TTY-ACM6, and I think it's 57600 is the baud rate that it uses. Yeah, so you can see this is binary data. This is the tap data being streamed back. So I've got a bug somewhere, and so let's track it down. So I'm basically either the command itself isn't being sent to the Firmata board. I might be sending the wrong command. Let's see, let me quit out of that. Yeah. And actually, I think I pressed the wrong command. Screen, sometimes screen is a little bit of a pain to quit. So I think it's still running, which is going to confuse things. Yeah, so let's kill 31881. Okay, so that should have stopped the process. Oh, that's weird. My keyboard is doing something funky. Wow, I'm pressing the up key. Yeah, killing screen sometimes does some funky stuff. Let's just make a new tab. This one's dead to me. Okay, let's check if it's running. Yes, aux grep screen. So, okay, no screen process running. Cool, we're back to where we wanted to be. So, let's see. So, something's wrong. It's still streaming the data, even though this stop tap should have been called. So I put in a print statement. Let's start from the top here in my Python code, see if the Python code seems to be working, and then we'll dig into the firmware and see kind of maybe what I didn't do right inside of there. So let's run my sketch again. Let's do the tap streaming, and I want to pass in dev TTY-ACM6. Oh, okay, so my port is busy for some reason. I think that's because I killed screen. I'm just going to unplug the board and plug it back in, which unfortunately is going to get us back into the state that we didn't want to have. It'll be in a good state now. Let's just check the serial ports. Okay, so it's TTY-ACM6 now. Let's run this. Okay, now connected. I didn't really kill screen in the right way. You're not supposed to send it a kill command. I always forget the key sequence, so I pressed Control-A, Control-C to quit at that time, and I think that actually like put it in the background or something. I think it's like Control-A, Control-K or something. I need to look it up later. So, okay, first time this runs, it runs fine. Now let's run my example again. Oh, actually, well, I just stopped it, and this is actually good. I can see my stopping was printed out, so I know for sure this is getting called. Let's go to my board, my stop tap function, and let's make sure that I'm doing the right thing there. And I think oh wow, interesting, I just lost a light here, so let me grab another fun thing about live streaming. So I've got a whole box of camcorder batteries here. This is, when you do a lot of video stuff, you run through batteries at an amazing rate. Let's see. Alright, we need a battery in here. And if you're curious too, these are the lights. I have two lights that are on me. These are actually in the shop. These are really nice. Let's see how to do this. So this is just an LED light. Takes a little camcorder battery. This is a Sony style battery here. And you can adjust the color temperature. So let me put a new battery in this one. And so you can see lights up now. Cool stuff. This is handy because I actually have a green screen behind me. That's kind of why I can overlay my head on here. But you need really good lighting when you're dealing with green screens. So, maybe if it's interesting enough to people, I can show off kind of the lighting setup I have here. So, okay, I think I just realized what my problem is. I remember I copied the code for stopping the tap from starting the tap. So I'm sure people that are watching this and probably saw me make this error were probably screaming as I went through all of this. But hey, it's good to show the debugging process. So I accidentally sent the stream on command instead of stream off. And that's probably what was going wrong here. So let's actually unplug and plug my board back in, because it's in a weird state where it's streaming that tap data forever, which seems to confuse Firmata. So it's good to learn kind of these things. So okay, let's run it once, and it's going to do its thing, and we're going to stop it. And then I should be able to run it again without it crashing like it was before. Let's see what happens. So it's going to read for 2 seconds, stop for 5 seconds, and then it's going to read for ever. I'm going to press Control-C. It called stopping. Now, in theory, that should call stop tap. That should now send the correct stream off function. And let's see if I can run the sketch again. And maybe we'll open the serial port again to see if it's streaming the data. So it looks like it got further. It's opening the serial port. I think we fixed it. And so it's running again, pausing for 5 seconds. And then it's going to receive data again. And just to be sure, I'm going to tempt fate. We're going to run screen again. And let's look at the output. TTY ACM6, 57600. And there's nothing there. And man, I'm trying to remember what the key sequence was. Was it this? Control A, Control K? Nope, that's not it. All right, we're probably gonna have to kill it the bad way again. Let's do Control A, Control C. Maybe it tells you in the man file. It's really annoying. Let's see if you impatient. Boy, there's a lot of stuff in this man file. We'll have to mess with this later. Now, unfortunately, it's still running. I think it must have like dumped me back out to the terminal. So if I look for screen, yeah, you can see this process here is still running. I don't know a better way to kill this thing other than just killing the process. So maybe you can send a signal, an interrupt signal, which I think this default kill is doing. So I don't know why it doesn't kill it in a more graceful way, but oh well. So all right, kill this thing. And then that's probably going to nuke this session for some reason. So we'll go back to this new one and unplug and replug the board. So okay, so we found the bug, we fixed it. So that's cool. And actually, the tap data is working. So we saw, we added 2 new commands. They're sub-commands to my custom circuit playground sysx commands. And they're just telling my code to flip on or off this stream tap value. And then when it's on, it grabs an accelerometer value and sends it back. So let's do the exact same thing for the accelerometer now, and not just the tap values. So let's make a new function or new duplicate of this. So we'll say accelerometer streaming. And let's set this up just like we had it before. And I'm going to pull out this tap before I forget. Oh yeah, I pulled it out of there already. So okay, let's do the exact same thing here. So let's stream accelerometer data for 2 seconds, pause for 5 seconds, then stream forever. So I'm gonna say, let's print this out also so we know what's going on. Streaming, how about printing accelerometer data for 2 seconds. And this function doesn't exist yet, but we're going to create it. So let's call board.startAccel and sleep for 2 seconds. And now let's print out pausing for 5 seconds. So it's called board.stopAccel, sleep for 5 seconds. And then I want to go in and do my main loop. So again, let's make this just like the other loop. So let's put that finally in here. and that's pull everything out. So let's do a try. And inside of here, I'm going to print out and say, okay, now printing accelerometer data, press Control-C to quit. This is always the thing. Whenever I write a program that's going to run forever, I like to print out and tell you, like, hey, I'm running forever, and here's how you stop me. Because I remember when I was learning Linux and a lot of programming and stuff like that, I would hate when I'd run something and then it would just stop, and I would have no idea how to stop it. So, you know, to me, it's second nature to press Control-C, and I know that that's sending a SIGINT interrupt signal, and I know that Python catches that and fails with a keyboard interrupt, but it's taken years to know that. So, you know, I try to be smart about making things a little more friendly and tell you, how to stop something. So now I want to start streaming again, and then I want to just do a loop forever while true and just sleep. I sleep for 1 second. You could sleep for 0, which just means give up your time slice to any other threads and things, processes that want to use it. But I don't even care about, I really don't want to do anything. It is important to call sleep here. You could put pass in, which is just not going to do anything. The problem is, and you're not going to notice it on modern computers that are like quad core and, multiple cores. This is just going to be burning resources. I'm going to be stuck in a tight loop, and maybe Python is smart enough. I don't know enough. I mean, maybe the pass function gives up a time slice, but this is just going to be stuck in a loop. I really want to say my program's done, like other programs, have fun, and that's kind of what time.sleep can do. So it makes things more responsive. If I didn't have that in there, I might notice like my mouse starts slowing down, like my CPU usage could rocket up. So it's just another smart thing to think about. Try to be nice to the users of a program. So okay, let's put in a finally clause again, and let's print out that we're stopping. And let's call board.stopExcel. And this is going to fail, but let's just run it. Let's see it fail because I haven't implemented those functions yet. But I'm kind of treating this like test-driven development, where you write your test, or in this case, my example, and you run it until it works. And so that kind of helps you build something kind of from scratch. And again, it helps you focus on what's important. Like, I really just need to implement this start and stop function. I don't need to, because those are the ones I'm calling in my example here. So let's call accelerometer streaming and dev ttyacm6. And this should explode after it connects because it's going to try to call a function that doesn't exist yet. So let's open the serial port, and then boom, attribute error. Circuit Playground has no attribute start Excel. This is one thing I don't like about Python. Its error messages really aren't the best. I mean, it's correct. It's true. It's telling me that the Circuit Playground instance has no attribute start accelerometer or start Excel. It would be nicer if this said, hey, you tried to call start Excel function on this object and it's not implemented. So it's just something a little prickly about Python that, the error messages, they're good. Like, this is enough information. Like, if I wanted to catch this attribute error and, do certain things, I could do that. But just as, a newcomer, it's kind of a pain for detecting that type of stuff, or it can be kind of confusing. So, okay, let's implement this thing now. I'm going to need to add a couple new subcommands. So let's kind of use these as a base. Again, I got in trouble because I copy and pasted stuff, so I need to be careful that I do everything correctly here. But again, it's nice that I never would have caught that bug if I didn't actually call my board stop function. So that's a kind of good example of like test-driven development, where you write a test and then you implement things and make sure that it actually works. So hey, I caught an issue because I was doing that. So okay, now I need to give these new values. So I'm going to need to go up to A and B because these are hex, so I can go up to 16. So okay, I've got these new values, and these functions are going to be exactly the same as my other one for the tap detection, but just slightly tweaked. So let's copy these, and hopefully I will remember to do everything correctly here. So start streaming accelerometer, data from the board. This is one nice little thing. So I'm using the Atom text editor. Control-Alt-Q will reflow a line. Super, super handy, because one convention in Python that's a little contentious, PEP8 is the Python extension proposal that defines the style for writing Python code. And the rule is 80 characters to a line. And I actually have a little ruler set up in Atom here that tells me this is where the 80th character is. And you can see, you know, I'm not treating it as dogma, like, and actually there was a really good presentation from PyCon last year from Raymond Hedinger, who's like a core contributor to Python. Awesome developer. Definitely like watch his videos if you want to learn about Python. But he basically made the case that PEP8 is good, but don't treat it as dogma. Like, there are lots of flame wars and things of like, oh, you're not PEP8 compliant because, you know, you're 81 characters instead of 80 characters. So like, if I wanted to fix this, what am I going to do? Throw the period on the other line, or like throw this whole other word over here? And his basic point was like, be flexible, you know, like it's okay to go over 80 characters if it's a comment here. Now, the intent of that PEP8 rule is that you don't write like really long functions that just run on and on and on. You have to scroll the screen to look at them. You know, if you do something like that, yeah, you need to step back and say like, why is this line so long? Like, how can I break this down and simplify it? But anyways, that's a little side rant. There's lots of things I've picked up about Python over the years that hopefully I can share some of the wisdom there. Okay, so I need to change my accelerometer callback because, again, I have to remember that callback so that my response handler can call it. So let me just make sure I get the right name for this. This is one thing also that I don't like about Python. Well, I'm on the fence about it. So Python is not a strongly typed language. You know, I can call functions and things that don't exist, and I won't know until I actually run the sketch. Whereas in like C++, if I tried to call a function on an object that didn't exist, it wouldn't even let me compile that code. And so there are drawbacks. Like, it's real fast to write code in Python, but it's also a little dangerous. It makes me a little uneasy sometimes, where, you know, that's why you have to be strict about testing Python code. Make sure you're exercising all of the code you wrote, because you don't know if maybe you know, typed the wrong thing here by accident, and you won't know until that code actually runs that it's wrong for it. So another little Python thing. So now I want to send my Excel. What did I call it? Did I actually call it Excel? Oh, Excel tap Excel on. That doesn't make any sense. How about Excel stream on? Yeah, let's change these. So an Excel stream off. Okay, so we save that. Let's go down and let's actually set. Oh, the person from PyCon, Raymond Hedinger. And actually, let me just, I'll Google search it real fast. Really awesome guy to watch his talks. I think they're all on YouTube. Yeah, Raymond Hedinger, Beyond PEP8. Awesome talk. Totally worth watching his stuff. And his talks, he's really good at covering things for Python programmers at all levels. Like, he doesn't dive into all the nitty-gritty details. Totally worth checking it out. So, okay, so I called that Excel stream on. I think stream. Did I call it streaming? Let's go back up and double check. Yeah, stream on, stream off. And, okay, so those are right. My Excel callback I'm setting here. In here I need to set my accelerometer callback to none again. And I actually need to change the name of these. So let's call this Start Excel and Stop Excel. Okay, save this. In theory, this should now work as far as it's going to print. It's not going to crash, but I haven't implemented that firmware yet, so we're going to come back to that in a second. Again, it's really a good idea as your program. Oh, see, I got something wrong here. Oh, interesting. So this is kind of telling me that my Start Excel function takes 2 arguments, but I only gave it 1 argument. So let's see. I must have written something wrong in this function here. So I forgot to give it the callback. Oh, and one thing you might notice is like this errored out and said takes 2 arguments, but 1 was given. And then you look at this code and you see, I don't see any arguments here. And this is another little thing with Python and Python classes specifically. Every function inside of a class has self as a parameter, which that gives you an instance of the class, so I can look at the variables I've set on the class. It's another thing that I don't like about the Python error message is like, This is super confusing. It's telling me that I gave it one argument, and then I go look at the code that's using it, and I don't see that argument there. And it's a little thing you kind of need to know as you learn Python more, just the way that its classes are structured. So let's see. Oh, it was the streaming example that I wanted to change. So I need to give it this callback. So let's send this. Now let's run this, and we should see it fail again. Well, actually, it shouldn't fail. It should just print out nothing. It's going to say streaming accelerometer data. We won't see anything. So yeah, 2 seconds. It's going to pause for 5 seconds, and then it's going to run forever and do nothing. But let's go in now. Oh, hey, I got something else wrong. Start Excel takes... Oh, I forgot that I was starting it twice. So see, this is good to go through and test things. Because I might have gone in and added that stuff to the Arduino Sketch, the Firmata firmware, and then my program starts failing for other reasons, and you have to start debugging things. Then you start wondering, like, okay, what did I break? Did I break something in the firmware, in the Python code? So do things in small chunks, and run test things often. Basically, is a very good piece of advice here. So okay, so we should see this thing run and print nothing for a while. So printing data for 2 seconds, pausing for 5 seconds, and now it's going to print forever. We can Control-C out of it. Okay, cool. So let's go back to the firmware, and let's do exactly like we did before. I'm going to need to create a Boolean that tells me if I should stream data, and use that to, inside of that loop, send the data. So let me copy out the new subcommands that I added. And let's set these as defines. And let's make this valid code. And just to be nice, I like to comment, like right now this is effectively the documentation for my Firmata protocol. What I'm going to eventually do is like do a real guide on this and actually document this in a nice to read way. But I like to have one spot that's just telling me, like, here are my commands. Here's exactly what they do. Here are the parameters you should pass into this command, that type of stuff, so that it's a little easier for another person to look at this and kind of know what's going on without having to dig through all the code. Because as you saw, you have these huge case statements. You have to know a little bit about this code to really start reading it. So turn on continuous streaming of accelerometer data, and let's turn off, oops, make that line up. Turn off streaming of accelerometer data. So, okay, I know I'm going to need another Boolean variable here, global, to say stream Excel, and we'll default it to off. And then in my main function subcommand processor here, I need to add in a couple of case statements now. So case cp excel stream on. And I actually don't need these braces because I'm not actually setting any local variables. I'm just manipulating this global variable. So I don't technically need these, and I think it makes it a little harder to read. But like I said before, I think as the next round of refactoring, I should go in and make these all explicit functions. So stream on should set stream Excel equals true. And very easy error to make when you have case statements, switch statements. Each of those cases needs to break, because if I didn't have this break and this tap stream off gets called, it's going to fall through and actually call all of the case statements below it. And sometimes you want that logic. Like, there's a lot of programs where that simplifies processing of stuff, but in most cases you don't want that logic. So if it's a very, very easy bug. I think I've made it a million times myself. So I'm going to say stream Excel equals false and break out of here also. Since this is the last statement, I don't technically need this break, but it's smart to always get in the habit of, as soon as you write a case statement, even before I write this line of code here, I should just immediately write the break statement, because I'm going to come in later and add another statement below here, and if I forget that I didn't break out of this one above, I've got a bug there and I've got all kinds of problems. So little bit of advice when you're writing kind of complex switch statements like that. So okay, wait, let me go back up. So this looks good. stream on, stream off, set that global variable. Now let's go down, and just like I did for the tap, let's check if an accelerometer event should be streamed to the Firmata client. So exact same logic. I'm putting in the same place. It's going to use that same sampling interval to control it. So we'll say stream accel. If that's true, now I want to go in and put my logic to send an accelerometer response. So let's scroll back up to where I had that. And this is, it's a big sketch, unfortunately. Yeah, here it is. Okay, so my accel read function, accelerometer read, I'm going to copy this out. And again, red flag is going off in my mind, or alarm bell, that I've just copied and pasted code. You know, that's a signal that I should put this into a function and call that instead. Maybe once I get this example working, let's do that, because it's nice to do a little bit of refactoring like that. I'm just going to try and make this all line up, because that's another common thing. It's easy to leave code messy, and the problem is when you've got a 1,000-line program like this, messy code is a major problem when you're trying to read it and understand what you're doing. One nice thing about Python is that it's all based on white space, which makes it easier to read. So like, you know, each block has to be indented or it'll fail. You know, you don't have to do that in C code or Arduino code like this. So it's good to just make things line up, make it, you know, I can look at this code and know, just based on the amount of white space here, that all of these lines of code are part of this stream accel check. You know, there's nothing stopping me from putting this out here. Now when I look at this, my eyes are like, oh wait, it's next to the if statement? Is it called after this? So, you know, it's good to use indentation where you can. Okay, so this should be good. I'm just constructing, I'm reading the accelerometer, and actually, oh, I think I just deleted something on accident, or I didn't copy out all the data. So let me go back and make sure. Oh no, sorry, yeah, I don't need it. This doesn't actually return a result. You call the read function, and then it actually sets these properties on the class with the last reading that it got back. So okay, let's save that. Let's upload it to my Firmata board. So I've updated the firmware on here, and now we should see this stream out the data as fast as possible, and it'll do it for 2 seconds, it'll pause for 5, and then it'll do it forever if we got everything right. So let's see what happens. Yep, so we're going to stream a bunch, pausing for 5 seconds, and we're going to stream a bunch after this. I'm going to press Control-C. Now I'm going to run it again, and let's see if it fails, because that tells me that it still might be listening, or still might be streaming out data, like we saw it kind of fail before. And this will test if the board stop is actually working here. Yep, it looks like it's working. It didn't fail, so we'll let this run. Cool. Okay, so that works. So that's cool. So I've just gone through adding new commands to Firmata, and plugging that into a little Python wrapper around the PyMata library. And so that's basically what I wanted to show here, was just dealing with how to use Firmata, how to extend Firmata, because there's not a lot of info on that out there. You kind of have to read the Firmata protocol and learn about all the different libraries and things. Just to scratch a little itch that I want to do, let's pull these out and put them into explicit functions that send back data. So let's copy out my accelerometer, and let's make a function. I'm going to throw it above the loop here, but I probably should put this in a different spot later. But let's say send accel response, we'll call this, and let's put a comment above here. Read the accelerometer and send a response packet. And let's just put in the code like I had it. And of course the spacing's all messed up, but that's okay, we'll fix it real fast. I don't know if the Arduino IDE, I don't know, let's look and see if it has a, well, okay, I can probably do this. A lot of IDEs have a really nice function to automatically format the text, just based on, like Atom has it, where if I don't format things correctly, and I can't remember where it's at, Atom has so many things, you can basically say, I want to auto indent a line, and it'll indent the line where it thinks it should be indented. Arduino doesn't have that, but they do have decrease indent. So Shift Tab. So I decrease this all the way and then tab it. Oh, it looks like, yeah, I didn't even get these ones correct. So let's fix these lines too. So decrease the indent all the way and then one indent. So, okay, that's a little easier. Okay, so I've got my send Excel response. So let's actually call this function then down below here. So now this, look at how much simpler this is. And it logically makes sense because I want to check if the accelerometer event should be streamed, and then I want to stream it. So if stream Excel is true, send the accelerometer response. It's nice when you have code that you can kind of read and actually make sense. That's what you really, or what I really try to strive for a lot of times, because it just makes things easier. As you get more experience programming, you're going to realize that there's an initial hump of learning a language and how to use it, but the vast majority of things that experienced programmers do are things that help them maintain code and write code and read code. It's not knowing all these tricks of how to use a language and every little detail. It's really knowing how to write code that you can come back to 12 months from now and realize, oh, this is how I go and extend this. I don't have to read through all this stuff, because just looking at this block of code, I'm going to look at this in 6 weeks and not even remember what the heck I was doing. I'm not going to remember that I have this code block in 2 places. So that's really what you should strive for, is getting rid of all this cruft and making things really easy to read and understand again. Okay, let's come back. Let's add a new function. Void send tap response, and let's put this code in there, and we'll unindent it and then indent it, and this should be fine as is. And let's go down here and let's do send tap response. Okay, that's cool. Now let's change it in my main processing of all the commands here. So let's pull it out of here, and let's just call in this case statement. And actually, I don't even need these braces anymore because I don't have any local variables. So let's call send Excel response, and exact same thing here, but for the tap. Send tap response. Okay, make sure it compiles. That's good. Let's upload it. And I'm going to run the examples again, and they should work exactly the same as before. And this is another kind of test-driven development kind of thing where, I've got a test, I'm using that to verify my functionality, and that helps make you a little more secure about going in and changing stuff, because I might have just introduced a bug. When I copied these functions out, maybe I missed something here, or maybe there's some global state that I forgot I'm dealing with. So it's always smart, it can be kind of a thing where you get worried about refactoring code because you're like, man, what did I break? So it's good to have tests or things that can actually go back, exercise your code and say, okay, it's running fine. So, I don't feel so bad about refactoring things and pulling things into functions, because I know I can run this little test here, this example, and if it works, I know I did things correctly here. So let's see what happens. This should just stream the data for a little bit. Yep, it's streaming it. Pausing for 5 seconds. It should stream it again. And then what I'm going to do is I'm going to run the non-streaming version of this example, just to make sure that I didn't break that too. So this one is just calling that read Excel function explicitly every time. So let's pull this one. Let's see, accelerometer. And so this should every 2 seconds print out an accelerometer reading. And this will just help us be safe in knowing that we did the right thing. So yep, it looks like it read it. So clear that. And let's do the same thing for the tap detection. So let's run the non-streaming one first. I think I called it, tap.py. And this will print out the tap sensor data every 2 seconds. So yep, OX0. Now something, and I think this stream has probably gone on long enough, but maybe another stream, I want to make this a little simpler, because right now I'm just giving you back the value of the tap register. A user of this code doesn't care about that. I don't want people to have to know, like, oh, if this bit is flipped on, then it detected a tap. So I'm actually going to add that to my Circuit Playground class later, where, you know, when it calls the accelerometer callback and the tap callback, I'm going to do some processing. Like, I'm going to convert these values into meters per second squared and stuff like that. So just make things a little friendlier, because this Circuit Playground class is meant to be like a higher level class. It doesn't show you all that low level stuff. It's meant to be a little bit easier. But for now, I'm just trying to get this stuff working and kind of show how to extend this stuff. So we'll just keep it with this. So, okay, so the tap worked, and let's do the streaming version and make sure this one works too. So this should print out for a couple seconds and then pause and then print out in a loop. So it's connecting. Yep, prints out tap data, pausing for 5 seconds. And I'm actually going to tap the board a little bit in the next. So you can see, like, as I'm tapping the board, we're getting little streams of values here. There. So, okay, so I'll just stop it. So let's see. Oh, that's interesting. It failed attempting to use a port that is not open. That's kind of interesting. So, and I noticed that it stopped printing stuff for a second there. So something was wrong. Let's see if that reproduces itself. I'm going to reconnect the board. This might be a bug that I need to track down later. So let's see what happens here. And I think what was happening was it was trying to call the stop streaming command because it hit that finally loop, or that finally clause. And to send that command, the serial port has to be open. So something caused, oh, and it might have been because when I was tapping the board, I might have like accidentally shorted something out on here. So yeah, so I'm tapping it now, and you can see little spikes where it's sending the data. So cool. So I'll pause that or kill that. And I think that's it. I think I'm going to end the stream here. This is, you know, an example of adding a couple new commands to the Firmata example. So, you know, Circuit Playground's not out yet, but I've got the code up here on GitHub so far, and I'll push up the examples I have. You know, I want to have a really nice and easy to use Firmata firmware that exposes all the functionality of the board. So, you know, stuff like the light sensor, the temperature sensor, lighting the neopixels, that type of stuff, reading the accelerometer data, so that then people can make real simple Python sketches, you know, like these, that call these functions like set the pixel, and it goes in and does the right thing here. So cool. Now one little special treat for the end. Unfortunately, OBS, it's got some kind of bug. It can't play a video. I made a little intro that I'm going to try to get working with the stream next time. But let me go in here and grab this little intro video. This is really funny. There's another bug in OBS, unfortunately, where it won't play my desktop audio. So I'm going to play a video, but I have to hold my microphone up to my speakers, and the audio quality might not be great, but that actually kind of fits the theme of this video. So let me find where I put this thing again. Let's see. Yeah, in here, and it's this one. Okay, so let me pull this over, and let me turn off the, let's go purely desktop mode here. So, okay, and we'll full screen that as much as we can. Now I'm going to hold the microphone up to my speakers, so hopefully we'll hear things. All right, this is the hopefully the future intro to the live streams that I do here. So watch this. All right, nice. So bonus points if you know what this was inspired by. Hopefully should be pretty obvious if you were a kid that grew up in the 80s and watched a lot of science television and things like that. So, but it's a fun little thing. You know, I love these little retro videos. Boy, how do I quit out of the movie? All right, there we go. So fun thing. Hopefully I'll have that working in the later streams. Let me put my head back here. So yeah, that's just a fun little thing. So I'll look real quick if you have any kind of questions here. And yeah, throw out some questions, and then otherwise we'll kind of call this a day for this stream. And as you saw, there's a lot more stuff to do with Circuit Playground Fermata. You know, like I said, I want to make the this class here a little easier to use. Like right now, you know, I'm passing back the raw tap register value. I should go in and actually detect and see, you know, was it a single tap, double tap? So that's some stuff I want to change. There's, let's see, the capacitive sense functionality. So on the Circuit Playground board, you can actually treat most of the inputs as capacitive sense buttons, where, like, you know, you connect a wire to it, and then if you touch that wire with your finger, it can sense that as a press. So I don't have any of that logic in. I'm probably going to have to add some extra custom commands for that one. And then, like, the light sensor and the temperature sensor, I want to convert those from the raw ADC values to, you know, the actual like temperature value. The light sensor, I don't know if that gives you like a value that you can map to like lumens or something like that. So that might just be a raw value that's kind of low when it's dark and high when it's light out for it. So let's see. So I don't think there are any questions. So cool. Well, thank you for joining this live stream here. I hope you learned a little bit about Circuit Playground, Firmata, and Python. Subscribe to the YouTube channel to see this video and other cool videos. And then subscribe to Twitch, because that's where I stream to. I don't have the bandwidth to stream to both Twitch and YouTube at the same time. So that's kind of why this is like maybe a Twitch exclusive thing. But I'll upload the video back to YouTube so people can see it later. So thank you very much. And unfortunately, the cat cam at the end is empty. So she jumped out. She's gone. But that's it. Thanks a lot, folks, for watching.